Okay, hi everybody, Mrs. Pesic here, and we're looking at some continuation problems on section 3.4. I am live with 5 students who are going to be participating a great deal, and as a matter of fact, I want you guys all get up and move so you're sitting closer.
I'm pretty much in the odd one out here, so.
Why are you the odd one out?
I feel like I just move one space to the right. I'll just be like really close.
There you go. Everybody's moving up. All right, move up. Okay, so we're looking at number 10. This is on the 3.4 gift. If you didn't get a 3.4 gift, you probably want to stop by and see me. Otherwise, you can feel free to copy these problems down. So we're looking at number 10, and we're solving for t in this exponential equation. So here we go. You're all lined up. So I don't even have to pull popsicle sticks. I'll just point to random. All right. Griffin, first step in solving for t.
Well, you see here, you would subtract 4.
All right, I'm going to subtract 4 from both sides. So I get 6 times 2 to the t plus 5 equals 7. Next step, Matthew.
Divide by 6.
All right, dividing by 6. I got 2 to the t plus 5 equals 7. 6. Next step, Matthew.
I think, should we put it in logarithmic?
All right, what's it going to look like?
It's going to be log to the base of 2. Yeah. 2 equals to 7 of 7 6
Of 7 6
equals t plus 5.
equals t plus 5. All right, and then our last step would be what, Nathan?
Subtract 5.
Subtract 5. So I'm going to get log to the base 2 of 7 6 minus 5 is my value of t. So this would be our exact answer. You could get a decimal approximation for this. And I probably should pull up my...
4.78. Is the
What is it?
negative 4.78.
Negative 4.78. Can we have independent confirmation of that? Do we agree?
This is so much fun.
Yeah, negative.
Yes.
All right, all good. Okay, let's move on. So now we're looking at number 11. So for number 11, if we are trying to solve this equation for x, this one, I think the strategy could be to make a substitution. Like, let's let u equal e to the x to make this a simpler problem. If I have e to the 2x, would you agree that that's e to the x quantity squared?
Yes.
Okay, so how can we rewrite this using u instead of x? Matthew?
U squared minus 7u plus 12.
All right, and then we're going to need to solve this. It's a quadratic equation. We can factor this. What's it factor into?
U minus 3 minus 4.
U minus 3, u minus 4. All right, and I solve and I get u equals what, or u equals what?
U equals 3, u equals 4.
All right, so remember that's good, but we want to find out what x is. We're trying to solve for x. So that means that 3 is equal to e to the x, or 4 is equal to e to the x, right?
Great.
Okay, and now we need to solve for x by doing what, Maddie?
Could you put it in logarithmic form?
All right, so if I'm going to rewrite this in logarithmic form, it's going to look like what?
Log to the base e3 equals x.
Log to the base
And then-
3, log to the base e of 3 equals x, which
Yeah.
is ln of 3.
Mm-hmm.
So ln of 3 would be one answer, and then what answer were we going to get from this?
Log to the base. Oh, you could just put ln 4.
ln of 4. So those should be our 2 solutions for this problem. Are we okay with this one?
Yes.
Okay. This one, I think, too easy for you. You could do this one, right?
You know, that looks really easy.
All right, let's move on. Let's try this one. Too easy for you?
Too easy.
What would you do to solve this one?
1-to-1 function.
1-to-1 function. So what are you going to write?
3x plus 2 equals 6 minus x.
3x plus 2 equals 6 minus x, dot, dot, dot. Solve that one. And let's move on to this one. For number 14, maybe not too easy, but not too hard either, because we can rewrite the left side using one of the properties of logarithms that we learned last class. So what can we write? They're both log to the base 3 here, log to the base 3 with a
You
subtraction.
could do log to the base 3 of 5x plus 13 over 6.
Like this,
Yeah.
equals log to the base 3 of 3x. So Matthew is using the quotient property, all right? Now what? Now use the 1-to-1, so we can say 5x plus 13 over 6 equals 3x. And again, I'll say dot, 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 because this is a nice linear equation. You can multiply both sides by 6, combine like terms, and so on. Are we okay with this? All right, and let's try this one, number 15. Nathan, what would be our first step in solving for x here?
Could you put the ln to log base?
You can. So we have 6 plus 3 log to the base e of x equals 4, then what? Trying to get,
Subtract 6.
all right, subtracting 6 from both sides. I get 3 log to the base e of x equaling -2. Then what, Griffin?
Well, you see, you need to divide by 3.
Dividing both sides by 3, I get log to the base e of x equaling -2/3. Then what? Maddie?
I switched it out of log form and then I put e to the -2/3 equals x.
All right, and that would be our answer, our exact answer, e to the -2/3. But you can always get a decimal approximation for that as well. And it did say approximate to 3 decimal places. So what would that be?
0.513.
Do people agree with that?
Yeah.
So x is approximately equal to 0.513. Okay. Too easy?
Yeah.
Yeah. What would you do?
Divide by 3.
Divide by 3.
Yeah.
And we
And
get
then
3, so log 4.
So I'm log to the base 4 of 6x equaling 3, and then what?
Put it into
exponential.
Exponential form. So what am I going to write?
4 to the 3rd equals 6x.
Okay. And you get what? 64 then divided by 6?
Yeah.
Dot, dot, dot.
Yeah.
I like making my dots a little bit bigger. Actually, so you can
Sign with dots.
all right. Do you have this one on your gift?
Yeah.
Yeah.
Number 17? Okay, so for number 17, it says log to the base 10 of x plus log to the base 10 of x minus 9 equals 1. So what can we do to solve this one? What's that?
Product rule.
Product rule. So how are we going to rewrite it using product rule?
Log of 10. Log into the base 10 of x times x minus 9.
Do people agree with that?
Yes.
All right. And then what would be our next step?
Multiply it out. Boil it out.
Oh, you could, sure. So we can get log to the base 10 of x squared minus 9x equals 1. Then what?
Should put an exponential.
Exponential form, which is going to be what?
10 to the first equals x squared minus 9x.
All right. Then what?
Subtract the 10.
Subtract the 10 from both sides. So I'm going to get x squared minus 9x minus 10 equals 0. Does that factor?
-10 and 1.
So I get x minus 10 and x plus 1.
Yeah.
And so my solutions are going to be
X equals 10, x equals 9.
let's stop for a minute though. Because I'm a little concerned that one or both of these may be extraneous. So we should check them in the original. Let's try 10 first. If we're testing 10 in the original, which slide this bad boy down here. Yes,
Can we
question?
just throw it in the log base 10x squared minus 9x?
Nah, I would go back.
Back to the original?
I would go back to the original whenever you're testing something. So I'm doing a little check here. I'm checking x equaling 10. So I got log to the base 10 of 10 plus log to the base 10 of 10 minus 9. Is that equal to 1? Question.
Yes.
Yeah.
Does it work?
Yes.
Because this is equal to what?
Yeah, well,
1. And this is log to the base 10 of 1, which is 0. So I get 1 plus 0 equals, so we like this solution. It checks out.
I love it.
All right, can we test, what, negative 1?
I don't think that one works.
You don't think it's going to work? So that one, we're checking x equals negative 1. I got log to the base 10 of negative 1 plus log to the base 10 of negative 10
Yeah.
is equal to, what's wrong?
You have a negative.
All right, so we're not allowed to do this?
No.
So this does not exist, does not exist, neither does this one, right? Okay, so this is gonna be an extraneous solution. So be on guard, okay.
Wait, so why do we have to, like, how do we know if there's an extraneous solution gonna be in, like, the solutions that you get?
I think you have to worry about extraneous solutions in this case because we ended up with a nice quadratic equation that has a domain of all real numbers. But our original problem, which I dragged down to the bottom of the page, but this original problem here does not have a domain of all real numbers. In this case, the domain for this piece is x has to be strictly greater than 0. And the domain for this piece would be what? X minus 9 is, x has to be greater than 9. So overall, my domain for this entire problem, I have to take this more restrictive one. So my domain for this problem is x has to be greater than 9. And one of my solutions was not greater than 9, right?
Greater or equal to 9?
I would say strictly greater than, because
Okay.
if I plug in a 9 for x here, I would get log to the base 10
Okay,
of
all right.
0. Not allowed to do that.
All right.
All right, thank you, Nathan, for asking that. That's a good question for why. So that made me formulate my reason for why we can tell whether this is going to be extraneous. Okay, is this the next one that you have?
It is.
That looks really tiny. Good thing you guys all moved up front. Okay. You've deposited $1,000 in an account that pays 6.25% interest compounded continuously. How long will it take your money to double?
Could we throw this into a graph when we get the formula and then just,
Should we use the PERT formula?
I would use the PERT formula.
okay.
So that's A equals P times E raised to the RT. What can we plug in here?
Your P would be 1,000.
All right, P is 1,000.
Your E is E.
E is the real number. E is approximately 2.718.
Your R is 0.0625.
Do we know the T?
No, that's what we're looking for.
No, that's what we're trying to find out, right? But we want to know how long it's going to take for our money to double.
So it'd be 2,000.
So I want to find out when is my amount going to be 2,000 if I started with 1,000. So we need to solve this. How are we going to do that?
Divide by 1,000.
Divide both sides by 1,000. So I get 2 equals E to the 0.0625t. Then what are we going to do?
Should have put it in log.
So we're going to rewrite it in log form.
Yeah.
It says log to the base of 2 equals.
0.0625t.
All right, and then we're going to have to divide. All right, so we get log to the base E of 2 over 0.0625 equals t.
Could we ln of 2?
And you could use ln of 2. So really, we could say ln of 2 divided by 0.0625, and that turns out to be what?
I got 11.09.
11.09?
Yeah.
So
11.1.
about 11.1 maybe?
Yeah.
So it's going to take approximately what?
11.5 years.
So it's going to take 11.1 years for money to double your money. Are we okay with this? 11 years to double your money.
That's a lot of time.
Yeah, so I mean, if your interest rate is higher, will it take more years or less years? Less years. Okay. All right, let's see. Was there more? Yes. All right, let's take a look at number 19. All right, this is the last one, and then we're going to look at some things from section 3.5. The number Y of endangered animal species on a protected wildlife preserve from 1990 to 2004 can be modeled by this natural log equation, where T is between 10 and 24, where T represents the year, with T equals 10 corresponding to 1990, during which year did the number of endangered animal species reach 342? Matthew.
Alright, so I'm gonna guess we're gonna graph this. What?
I'm gonna go with a algebraic solution.
Oh, wait, we can just,
We're gonna solve the equation algebraically. But we certainly could maybe take a look at the graph after we do that.
alright, so,
Should we do 342 equals
So where are we plugging in the 342?
for the Y?
For the Y, because that's the number of animals. So we get 342 equals negative 117 plus 159 ln of t. I am going to pause this and give you guys a chance to work on this on your own. So if you're watching, go ahead and pause this also. Hello? There we go.
7.935, but
Okay, so we're back recording now. Hopefully you had a chance to try this out. So what were our steps? What do we do?
Add
Add
117.
All right, adding 117, so we get what?
459.
459 equals 159 ln of t, then what?
divide 159.
Dividing both sides by 159, what decimal did you get?
we have,
2.89.
Yeah,
Either one, you could leave it as a fraction or write it as a decimal.
2.89.
2.89 equals ln of t, and then what? So 2.89 equals log to the base e of t,
Yeah.
then what?
Exponential.
So e raised to the
2.9.
2.89 is equal to t, which was approximately what?
17.9.
17.9. So it's going to take about, what, 18 years? Does that make sense? And so what year would that correspond to?
98.
1998, because t equals 10 corresponds to 1990, so t equals 18 would correspond to 1998. Are we okay with this?
Yes.
All right, and I think that's it for this. Yeah. All right, so what we're going to do now is we're going to take a look at some things in section 3.5.
It's going to be a long lesson.
Okay, but I have a gift for you.
Oh,
Yay.
yay.
Love the presents.
Nothing like double gifts on Friday.
Nothing quite anything like it.
It's definitely something.
I don't feel more alive when I get 2 gifts today.
Can I have a
What could make it better might be 2 gifts and a practice test.
Oh.
Or we can wait until Tuesday for the practice test.
I think we need to give myself a heart attack.
Too much?
Okay. I have huge
All right.
after school.
So our learning objectives in section 3.5 are to use exponential growth and decay functions to model and solve real-life problems. And also to use Gaussian functions, logistic growth functions, and logarithmic functions to model and solve real-life problems. So there are 5 common types of mathematical models that involve exponential and logarithmic functions. And I have them on your gift for you. They look like this. This first one is an exponential growth model. It looks like this. Y equals a times e raised to the bx. You know what exponential growth functions look like. They start out like this, and then they grow very rapidly. All right, so that would be an example of an exponential growth model. The exponential decay model is going to look the same way, except it's going to go the other direction, right? Exponential decay, all right, would be this one, okay? And then we have this Gaussian model. the Gaussian model, they have the pictures of these on page 257 if you want to look at better graphs than I can draw. The Gaussian model, if you're looking at page 257, that's the one that kind of looks like a, like maybe like a bell-shaped curve. Have you heard of bell-shaped curves?
Yeah.
So something like this, right? All three of these, the exponential growth, the exponential decay, and the Gaussian model, they all have what in common as far as the asymptote is concerned? Horizontal asymptote, just one horizontal asymptote, and it looks like unless you change things around, it's going to be at
0.
y equals 0. Okay. Then we have the logistics growth function, which the logistics growth model is also there on page 257. That one's kind of interesting. That's this function here. I'm trying to circle that one. And that one is a case where the graph starts out kind of level, but then rises very, very rapidly, but then it starts to slow down its growth and level off at some number. So this one actually has two horizontal asymptotes. All right, that is the, what are we talking about, Gaussian model. Okay, then, no, I'm sorry. I'm circling the wrong one. The Gaussian model is this one, right? I'm talking about the logistics growth model. I had the wrong one circled. So the logistics growth model is this one here. That starts out pretty level, then rises very rapidly, then starts to taper off. Okay. And then lastly, we have the logarithmic models. And you know that the logarithmic models that we have here, those graphs look something like this. And what's unique about these that the other guys did not have? Vertical asymptote. So in this case, vertical asymptote at, x equals 0. But if we're going to be shifting this left or right, then the vertical asymptote will change. Okay, so we talked about the vertical asymptotes and so forth. Let's take a look at this problem number 1 on your gift. It says the population P of a city is given by P equals 95,300 times e to the 0.055t, where t equals 0 represents 1996. According to this model, when did the population reach 150,000?
Is this the first one?
So what are we going to do?
We plug in 150,000 for P.
Plug in 150,000 for P, and then solve, just like we've been solving problems earlier in this lesson, right, from section 3-4. So if I plug in 150,000 equals 95,300, e to the 0.055t. All right, I'm going to pause this video while you take a little bit of time to solve this for t. Okay, let's talk about what's our technique here. If we're solving, what's our first step?
Divided by
95.
All right, divided by 95,300. What decimal did you get?
1.57.
Yeah.
1.57
Yeah.
equals e to the 0.055t, then what?
Log it.
All right, so you're going to rewrite this in log form. So it's going to be log to the base
E
of
1.57.
equals
0.055. No, P, yeah, that's right. Yeah.
0. No.
0.
No.
5.
Yes?
T.
Yes.
Yes.
Yeah.
0.055t. Are we okay with this?
Yeah.
Oh, I see.
So that's the same as ln of 1.57 equals 0.055t. Then what?
Divide the
I divided the same thing.
Divide both sides by,
0.05.
okay? So those are dividing out, so we end up with t is approximately what?
8.2.
8.2. And so what's our answer to this question?
Oh, this is math.
Oh man. Okay.
2004.2.
Because t equals 0 is 1996, so 8 years later would be about 2004?
Yeah.
Are we okay with this? Okay. Okay, so let's take a look at a different type of problem. This one, you're not given the growth model, all right? And this one's not on your gift, all right? So this one you have to take some notes. In a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. So how many flies will there be after 5 days? If this is following the law of exponential growth, that means we're going to need the model that we saw. Let's go back to the model, exponential growth. So you know where I'm coming from. Here's our model for exponential growth, right? So I want y equals a times e raised to the bx. So I'm going to use y equals a times e raised to the bx. After 2 days, there are 100 flies. Days, flies. 2 days, there's 100 flies. 4 days, there are 300 flies. So think of those as like your ordered pairs, if you will. Agreed? So days is x in this model, right? And y is what? Number of flies. So I can plug in 100 equals a times e raised to the b times 2. You with me?
Oh, I see it.
And so I can plug in the 300 for y and 4 for x, right? And I think what might be helpful for us in this problem is to solve for a in this first equation. So if I divide both sides by e to the, I can call this e to the 2b, can't I? B times 2. So I'm going to divide both sides by e to the 2b. This divides out with this, and I'm left with an expression that is a equals 100 over e to the 2b. All right, so then I'm going to take this expression for a, and I'm going to pop it in right here, and that's called substitution. All right. So what do we have now? What equation should I be writing, Maddie?
300 equals 100 over e to the 2b times e to 4b.
Okay. If you would like, you could think of this, you know, this is like over 1. So this is really 300 equals 100 e to the 4b over e to the 2b. If I'm dividing two things like these guys right here that have the same base, what do I do with the exponents? Add, subtract, multiply, divide. Subtract. So I'm really going to have 300 equals 100 times e to the what?
Let's see.
2?
Yeah, 2.
2b.
2 or 2b?
2b.
Because I want 4b minus 2b. What's 4b minus 2b?
2b.
Are you just pausing or?
It's 2b.
Is it 2b?
2b?
Yeah.
Okay.
Yeah, the biggest part of it.
That's what I've been saying.
Yeah.
All right, so that's 2b, agreed? 2b or not 2b, exactly. All right, so in this case, we're going to have to divide both sides by 100. And so we get 3 equals e to the 2b. I'm going to pause this for a moment while you solve for b. It is, isn't it? Okay, so we're rewriting this in log form.
Yes.
So we're going to get log to the base e of 3 equals 2b. That's ln of 3 equals 2b. And so then we do what? Divide by 2. So our answer should be ln of 3 over 2. And that b value is what? Give me like 4 decimal places.
0.5493.
0.5493. People agree?
Yeah, I agree.
Okay, so that's great. And now that we have that b value, we're going to plug that in where? Right here to solve for a. So I'm going to plug in, what was it, 0.5?
.5493.
0.5493 is my B value, so I'm going to plug that in right here and solve for A. So I'm going to get A equals 100 over E raised to the 2 times 0.5493. Everybody with me?
Oh, it's 2B.
Yes.
Yeah.
So I want 100 over E to the 2 times 0.5493. You getting 33.33, something like that? Okay, so if A is equal to 33.33 and B is equal to 0.5493, I think finally we have our model, right? So I'm going to plug those values in the correct places. And so our model is going to look like y equals 33.33 times E raised to the 0.5493 x or t, whatever variable you're choosing to use. Are we okay with this?
And then we do 5 days.
Our hard-fought model, right? We have our model, and now we can finally answer the question that was asked, now that we have our model, which is how many flies will there be after 5 days, is the question. But we couldn't answer it until we had come up with a model. And so when you plug in 5, you end up getting how many flies?
519.
Do people agree with that?
Yes.
In 5 days, we will have 33.33 times E to the 0.5493 times 5, and that is approximately what? 519?
Yeah, 0.5.
0.5, 0.6, so about 519.6, I'll say maybe 520 flies. Let's not count parts of flies. Are we okay with this?
Heck yeah.
All right.
Is there going to be a question like this in the test?
I love this problem. This is a great problem. So where you have to write your own model, this is a good problem. So probably on the test, and you might even see it on the final exam.
Are we going to have to memorize
Memorize
these formulas?
The y equals a times e to the bx.
Yeah, and like no.
Like the
Let me think about whether I'm going to provide that for you or not. Okay, let's switch gears a little bit. Notice I left you number 2 on the gift for you to do yourself, because I'm so nice. Let's take a look at the top of page 260 in your book. It gives a little background to carbon dating. In living organic material, we're on the top page 260, the ratio of the number of radioactive carbon isotopes, that's carbon-14, to the number of non-radioactive carbon isotopes, carbon-12, is about 1 to 10 to the 12. That's in any living organic material, okay? But when the organic material dies, its carbon-12 content remains fixed, whereas its radioactive carbon-14 begins to decay with a half-life of about 5,700 years. To estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time, T in years. So this is a way of figuring out the age of something that was once living, right? So it's R equals 1 over 10 to the 12 times E raised to the negative T over 8,223. So the graph is shown. Notice that the R value is going to be decreasing as time goes on. All right, so let's take a look at the example that we have on the gift, which is number 3. It says estimate the age of a newly discovered fossil in which the ratio of carbon-14 to carbon-12 is R equals 1 over 10 to the 14. So we are going to be using the formula for carbon dating, which is R equals 1 over 10 to the 12 times e to the negative t over 8,223. And, okay, so what should we do? All right, substitute, yeah, we're going to plug this in right here for the R. So we're going to have 1 over 10 to the 14th equals 1 over 10 to the 12th times e to the negative t over 8,220. Then what?
The 1 over 10 to the 12 make those like negative 14, negative 12.
Multiply by 10 to the 12. On both sides.
Okay, you could rewrite these as negative exponents. Let's multiply both sides by 10 to the 12 to get rid of this one in the denominator. So this divides out with this. And what is 10 to the 12? I'm going to think of this as 10 to the 12th over 1 here, times 1 over 10 to the 14th. So I really have 10 to the 12th over 10 to the 14th. What am I going to do with the 12 and 14? Add, subtract, multiply? Subtract. So I really get 10 to the 12 minus 14 is a negative 2. Agreed? Which is the same as 1 over 100. So I now have 1 over 100 equals e to the negative t over 8,223. Does this look okay?
Does. And then could we say ln of 1 over 100?
All right, so we're gonna rewrite this in log form.
Log.
So log to the base e of 1 over 100 equals negative t over 8,223, or we can say ln of 1 over 100 equals negative t over 8,223. Then what?
Multiply by
8,223.
All right. Well, how about multiplying by a negative 8,223? Yeah.
Yeah.
All right, just be that way. Okay, so I'm going to multiply by negative 8,223 times ln of 1 over 100, and that's going to equal t. Do we agree?
Yes.
And can we get a answer for that? 37,000? 868? All right, let's go with, well, let's round to the nearest year. So we're saying that this recently newly discovered fossil would be 37,868 years old. Are we okay with this?
Could you do this in something that's living? Or no?
Well, but in living, the ratio is always going to be the same.
Oh, okay.
So the point is, you would do this on, like, I mean, what they would use for carbon dating? They might find some old piece of cloth or something that was made from wool, right? That was a, you know what I mean? And the wool was part of a sheep at one point, something like that. Does that make sense? Or you know, petrified wood, like in the petrified forest, they could maybe do this on that to see how old the, right?
So like you use this to like figure out how old like things are.
Yes. Yeah,
But they have to be dead.
it would have to be something that was alive at one point,
Okay. But it's not dead.
but is no longer. Yes. Okay. Okay, we're just going to do one last problem, and that is this. All right, let's see. The value of B in the exponential decay model determines the decay of the radioactive isotopes. Is this the one I wanted to do? Oh, yeah. Okay, so find how much of an initial 10 grams of radium-226 isotope, which has a half-life of 1,599 years, how much of that is going to be left after 500 years? Okay, so Hint, we need to find the equation first. This one is not on your gift, right? So you're going to put this one in your notes. So find how much of an initial 10 grams of radium that has a half-life of 1,599 years, how much of it is going to be left after 500 years? Matthew?
So should we set up a XY chart or no? Like the flies?
Well, before we think about that, can we remind ourselves about the exponential decay model? So that looks like this. So if I've got y equals a times e to the negative bt.
1100. Or 500 years for T.
Okay, so if I plug in 500 years for t,
10 grams in for A.
10 grams in for A, so I got 10 equals e to the b times 500. How much is going to be left? Remember, this part right here in our formula is going to be the amount remaining after t years. So after 500, wait, why would, oh, you know what? We can't plug in the 500 yet.
Plug in 1599.
Yeah, let's plug in the half-life,
And then
because we still need to find the, we know the A is the initial amount, right? But we need to find the B value. So we're going to plug in the half-life first. I'm not going to write half-life, I'm going to write time here, but we're going to plug in the half-life. So after 1,599 years, the 10 grams will be down to what?
5.
5. Does everybody understand why we're plugging in 5 for Y, 10 for A, and 1,599 for T? This is all so we can solve for B to write our model. All right, so I have that here, 1/2 of 10, blah, blah, blah. So I'm going to divide both sides by 10, and so I'm going to get 0.5 equals e to the negative 1,599b. I just rearranged those because I like to have my variable after the number. Okay, so I am going to pause this while you solve for that constant b. Okay, so for this, did you rewrite this in log form?
Yeah.
So we get log to the base e of 0.5 equaling negative 1,599b. So then did you rewrite it as ln? Did you divide both sides by negative 1,599?
Yeah.
And you ended up getting b value, give me like 4 decimal places. 0.00.
Oh,
0. 3 zeros and then
Give me one after that.
3.
So 0.00043. Okay, so that's our b value. So now I know that my model should be y equals, A is my initial amount, they're saying 10 grams, times e to the negative 0.00043 t. Agreed? Now we can answer the question that was asked, which was what? How much is going to be left after 500 years? So what do you think?
I don't know what it is. 'Cause it's the-
Did you plug in 500 for t? So we get y equals 10 times e to the negative 0.00043 times 500, and you got y equals what?
8.06.
8.06?
Yeah.
All right. Something like this. So 8.06 what?
Grams.
Grams. Are we okay with this? 8.06 grams remain after 500 years. Another great problem that you may see again. Okay, so I did say I'm going to stop at this point and follow more directions. Okay.